Please welcome to the stage Anumitra Datta Majumdar and Anubhav Sen.
Almost there. So this is the last talk. And after that, it's all open for fun and games. So today, myself and Anubhav, both of us from the LinkedIn House Security team, would be talking about building secure machine learning pipelines, the challenges and the security patterns that we have been following. Okay. So we would like to acknowledge the contributions from the various internal teams in LinkedIn, and also, of course, the House Security team, the larger team that we are a part of, for spearheading some of the initiatives and programs for securing the machine learning pipelines at LinkedIn. So the talk outline, we will be covering the major use cases of machine learning at LinkedIn, and basically the business use cases, the various phases involved in machine learning pipelines, and some of the nuances of the distributed infrastructure that backs those phases. We will then be going into some of the security risks and security solution patterns. And eventually, we also touch upon some of the scalability aspects that we have, issues that we have observed while applying the security controls to secure these pipelines. Okay. So the major machine learning use cases at LinkedIn. So we use machine learning to help members build network on the LinkedIn platform. Machine learning is used to predict relevant jobs to the various members on our platform. Machine learning is used heavily to predict and recommend feed content, things like articles, posts, to our members on the platform. And of course, last but not the least, we use machine learning to detect abuse like account takeover, fake accounts, harassment, and spamming on our platform. So what are some of the high-level phases involved in machine learning? We have the experimentation phase, where most of the time is spent by data scientists in performing feature engineering and problem formulation. We have the model training and evaluation phase, where the data that is prepped in the experimentation phase is fed in, and the model that has been authored undergoes training, and then the best model is scored and selected. In the model deployment phase, the best model that is selected in the previous phase is actually deployed into the infrastructure, production infrastructure usually, for the purpose of model serving and inference, which is the last phase. So currently, there is an initiative at LinkedIn called Productive Machine Learning, or ProML, where all these various phases are tied together through integrated workflows and tooling and libraries. And the main goal behind this initiative is to boost the productivity of the data scientists at the company, because currently, various teams within the data science organization use different methods for each of the phases. So the main goal of this initiative is to bring all those processes and tooling and pipeline components under a single pane of glass. And of course, the major security concern is our member data, protecting our member data on our platform from data exfiltration and unauthorized data access. So how does the ML flow logical architecture look like? So we have offline components in our infrastructure that primarily performs the experimentation and training phases. And by offline components, I mean these are jobs that are batched or scheduled in nature. We have components that bridge the offline and the online world, and these are mostly in the form of event bus, like in the case of LinkedIn, it is Kafka. And also there is a model artifact store, which is used to store and retrieve models. And of course, the online components, which are basically applications, and they communicate with one another over REST interfaces. And as a part of this online components, we have the model deployment phase and the model serving phase that run. So what are some of the security risks and challenges in each of these phases that I just described? In the experimentation phase, the major challenge is unauthorized data access and the data leakage. So as I was mentioning, like in the experimentation phase, various data scientists in the organization have a need to do feature engineering. So during the course of such an action, this like unauthorized data access is a risk that we have seen. And also, during that process, there might be a leakage of sensitive data into the less secure areas of our infrastructure. In the model training phase, the important concern is generation of intermediate data sets through automatic flows, which could be sensitive in nature and which might not have any associated audit trail, and may be flowing into the areas of the infrastructure that is less secure. In the model deployment phase, the main concerns are unintended model actions like model publication to production or test environments. And in some of the cases, the models themselves might be personalized and might be containing some member data. In that case, we don't want the models to leak member PII into less secure areas of the environment. And finally, in the inference phase, the major concerns are security misconfigurations, which could lead to a potential denial of service attack due to resource exhaustion, and also using vulnerable software components. There are lesser known theoretical attacks possible as well, like member inference attacks, where an attacker is able to guess the data sets used for training the model. So what are some of the controls and the patterns, security controls and patterns we have adopted? For the experimentation phase, the major controls are access control. And by access control, I mean both rule-based and role-based access control. In the rule-based access control is usually based on the attribute of the target that is being accessed, and the role-based access control is on the attribute of the source that is trying to access the target. And the rule-based access control is usually done in some sort of a uniform access layer, and where the rules can be enforced in an integrated manner. For the encryption control, we use both encryption of data at rest as well as encryption of data in transit. For encryption in data at rest, we have seen cases where we absolutely need to decrypt the data during the process of model training. So in that case, what we try to do is reduce the data in the encrypted state or in the decrypted state as much as possible, so that the exposure of the sensitive decrypted data is reduced. And the other control that we have been using is as a part of the rule-based access control is also like enforce rules so that privacy of the data sets doesn't get leaked. And what I mean by that, when multiple non-PII fields are combined, it shouldn't be leaking some PII field. And this is usually done in that data access layer that I just mentioned through some rule-based, through the enforcement of some rules. And The last one is the feature sensitivity annotation, where we do have an architectural component in our environment called the AI metadata hub, where various features used during the training phase are annotated for sensitivity, and it is contacted by various applications and tooling in the pipeline during each of the phases. During the model training phase, we have the encryption, as I mentioned, as in the case of an experimentation phase. And most of the training flows are more automated compared to the experimentation phase. And the thing to look out for in this phase is the leaking of PII during these intermediate flows, especially in the case of a complex multi-stage model. And we have also developed some in-house machine learning-based classifiers to go and detect for PIIs in areas of the infrastructure that it's not supposed to be in, and also do some monitoring or alerting based on that detection. In the model deployment phase, we use controls like dual verification, which is very similar to a code review process. Like the code cannot be checked in without a reviewer's ship it. So similarly, in the case of a model cannot be deployed to prod unless it has been reviewed and okayed by a second person. And usually these model deployment systems are accessed through an UI, and we enforce multi-factor authentication on that. The other control that we have started looking into is the model randomization control. And this is applicable more to personalized models, which could leak member PII data, let's say in the test environment. And of course, during the model deployment phase in the testing infrastructure, we must ensure that synthetic data is used instead of actual member PII. For the model inference phase, the major concern is security misconfiguration. And the way we proactively address this is through the running of security benchmarks that can detect low-hanging security misconfiguration issues, and then making sure it's configured according to the best practices in the benchmark. And also the other control is we typically want to segregate workloads in production based on the sensitivity level of the data that the model is handling. And the model health assurance, which is a part of the ProML initiative, helps us look into the model health or observe the model health over a course of time to look for performance degradation, like accuracy degradation issues over a course of time, which could suggest potential denial of service attacks that the model could be under. Now, going into some of the key challenges that we have been facing in our environment. So basically, using heterogeneous controls in our offline and online environment, like heterogeneous authentication controls in this case. So our offline environment, which is where all the offline training jobs run, are mostly backed by things like the Hadoop HDFS, Hadoop MapReduce jobs, Spark, etc. So the main method of authentication in this offline environment is through the use of Kerberos delegation tokens and block access tokens, using which all the compute jobs is able to distribute the workload and access data from the storage. In the online infrastructure, all our services communicate with one another over HTTPS-based connection, which uses mutual TLS. So now, when an online service needs to contact an offline job, to get data or for whatever purpose as a part of a flow that spans both the online and offline world, there is a translation problem. So the way that we have solved this problem is through the introduction of this service called the translator service, which goes and consults an identity management system to get the entitlements of the authenticator that it gets from the service, online service. And in this case, it is an X509 certificate. And then it decides whether to grant access to that principal or not and generates the token. And that token is used to complete rest of the flow to go and contact the offline jobs and the offline data. And through this means, a full user attribution or a full service attribution is established that spans across both the online and offline environment. Another challenge that we have faced in our on-prem environment is due to the tight coupling of the compute and the data tiers. Like, usually all these machine learning phases are heavily distributed environments. So it is, such a tight coupling can actually introduce some challenges when we are trying to apply security controls for authentication and authorization. And what I mean by tight coupling is, let's say there is a compute cluster that needs to go and contact a cluster that stores data during the flow of a training job. So the compute cluster relies on some host-level identity to identify the storage cluster, and then goes and completes the transaction. So this introduces the tight coupling. The way we would be solving this problem is through moving to the cloud, Azure, through an internal project called BlueHat. So as a part of that project, all these storage services are already available as Azure services, as well as the compute services are also encapsulated as Azure services. So the main job over here would be to come up with an access layer in which all the controls for authentication and authorization can be introduced in a scalable manner. And then the access layer can consult the identity layer to go and check for entitlements of the various principals. Moving over to deep learning pipelines. So we have use cases in LinkedIn, like each of those ML use cases that I was mentioning in the beginning. Currently, there is a trend, and that this is primarily to improve the model accuracy for each of those use cases, that data scientists are using deep learning. And this is because on the LinkedIn platform, there is a lot of text data, like member activity, member economic graph, member profiles. So all these data, text data, are taken and then vectorized through a technique called embeddings and fed into deep learning network, like convolutional neural network. And such an operation is computationally intensive, both in terms of hardware and software. So in order to scale those to that computational demands, there is a common pattern where we are seeing that there is a use of a lot of open source containerized software to boost the innovation and scale of use. And with that, having set the context of using containerized pipelines, I will hand over the rest of the talk to my co-presenter, Anubhav.
Thank you. So how does a machine learning container pipeline looks like? It just looks like any other application container pipeline. The only fancy thing here is for deep learning, we are using GPU cluster instead of a CPU cluster. So what are the phases? So in build phase, a container image is built for a specific machine learning workflow. For building a container image, the base image as well as system dependencies and any application artifact is packaged together, and which builds a container image. Once you have a container image, you will push it to an image repository. From there, a container deployer, such an orchestrator, will deploy the container on a container runtime environment. Once the container is running, a container management tool will manage the container for the availability as well as scale, as well as continuous monitoring, as well as for any vulnerability scanning. So on a high level, let's go through an offline workflow. Here, a data scientist authors a training service, a model training service on its laptop, then pushes it to a code repository, then builds a container image using Jenkins or any internal image tool, pushes that container image, or builds a container image using the base image as well as any system dependencies, and the code that data scientist has pushed to the code repository and pushed that container image to the image repository. Then to spin up a Kubernetes cluster, a training cluster, the data scientist can use a kubectl job and will trigger an API call to API server, which will in turn bring up the TensorFlow training cluster, which will fetch the image from the image repository, will train the model, and based on the data fetch from the SDFS cluster. And once the model is generated, it will be pushed to the model artifact store. In case of online workflow, now the model has been trained. Now it's ready to be promoted to the production environment. There will be a Kafka event generated. The model deployment component of the ProML workflow will consume that Kafka event. The model deploy executor will fetch the model from the model deploy artifact store and will stage the model on the Kubernetes cluster, which will pull the service image from the image repository. So what are the security challenges which we see in container environment? We enable data scientists to use images as well as system dependencies which they can download from external environment, but they pose a threat. They include vulnerabilities, and they can lower down the security posture of our environment. The other challenge is related to the insecure access, insufficient authentication as well as authorization. An example would be a Kube API server allowing anonymous access, as well as orchestrator allowing access not based on role, just wide open access. The other risk is inter-container network traffic. By default, any traffic between the containers within a host is not restricted. That means any container on that host can see the packets, all the packets. At the container level, these are more related to the runtime vulnerabilities. Any new components, any new vulnerabilities found on any of the containers which are running at the moment. And the last one is insecure configuration of container runtime. This is more specific to how we are configuring the container runtime, like containerd or Docker, which is running on the Docker, which is running the containers. An example would be allowing direct SSH within the container. There's allowing containers to run as a privileged root user. Host allowing containers to mount sensitive directories. So these are some of the risks we see. So what are the control patterns? At the image level, start from basics. Make sure you certify the base images, any system dependencies, as well as application artifacts. By certify, I mean perform benchmark checks against the base images, perform vulnerability scanning if you're downloading, perform vulnerability scanning against any external libraries which you are downloading from external sources. Any application artifacts should go through a security review. Download the external libraries as well as images from trusted sources. Trusted sources here being your trusted vendors as well as partners. At the registry level, make sure to encrypt all the communications to registry. Make sure to enable authentication based on a certificate or token-based authentication. Use a scrubber to scrub any stale images or any vulnerable images. By stale images, I mean any images which hasn't been used for a long time and may contain some vulnerable components. At the orchestrator level, segregate the cluster based on the workflow sensitivity. Make sure to create virtual networks for different sensitivity workflows. Enable audit login on all the user-generated events as well as requests. Log it remotely. Compare the configuration of an orchestrator with the benchmark check. These are start from basics. Do the basics correctly, then you can build on top of that. Use the least privilege access model. By least privilege access model is provision the access for the users based on their roles, and don't just widely allow access to all the containers on a host or all the services in an orchestrator. At the container side, certify runtime configuration. Make sure you apply resource isolation. Ensure SSD is not running on the container. Ensure the container is not running as a privileged user. Apply user. And the last one is user attribution. All the actions on the container should be attributed to a specific user. So let's revisit the same diagram with some controls here. Now you can see that any images which are being built goes through a benchmark image, benchmark check, as well as security and legal vulnerability scanning, and it's being logged. All the communication is over TLS as well as certificate authentication. All the secrets are, if you are using etcd for managing some of the secrets, those should be encrypted. Otherwise, use a key management system to store any secrets for application. Between Kubernetes cluster and the SDFS, it's Kerberos token-based authentication, and use a remote logger, for example, Kusto. In case of online services, the Kafka online workflow for machine learning, the Kafka event which was generated needs to go through dual verification, which means it needs to be peer-reviewed, validated, and user-attributed. All other communications are rest over TLS, as well as certificate authentication is applied. OK. So what are the key takeaways for building a machine learning security patterns? Segregation of infrastructure. Machine learning workloads are highly distributed in nature. So it's very important to apply security controls in a scalable manner, which means we have to define some security boundaries. Once we define the security boundaries, we can apply security controls on those specific boundaries which we have defined. The high-level guideline here would be to divide or segregate the machine learning pipeline environment into following three phases. Three: environment based on storage and computation tier, based on control plane and data plane components, as well as based on the workload sensitivity. Once you have segregated your environment or your infrastructure based on these three tiers, then you can apply security controls only specific to that specific tier. And it's easy to manage and scalable. AI metadata system, machine learning, the risks associated with machine learning are very specific to models. for example, model performance degradation, as well as a model learning PII during training phase. So it becomes very important to understand what sort of, what is the purpose of a model is, what sort of access that model has, like what sort of access, what sort of features that model is accessing, as well as the data. And it becomes very important to maintain a metadata system which will have association of all this information, as well as sensitivity annotation of each and every feature used by that model, so that controls can be designed as well as segregated based on that information. Monitoring, continuous monitoring is important. Make sure whenever you're designing your ML pipeline security patterns, you are applying the concept of continuous monitoring. That means you're scanning your environment regularly for any vulnerabilities, monitoring the infrastructure for any specific performance degradation, because that's one of the major risks in machine learning pipelines, as well as collecting as many security metrics as you can to design controls. Security infrastructure. In ML in pipeline, there are two key security infrastructure components. One is identity and access management, and the other is your key management system. So make sure whenever you are designing your security infrastructure, that should be scalable and highly available. Any design should incorporate the concept of automation. That's where the security control scaling comes into picture. All the controls we have spoken about, or what Anamitra has spoken about, should be automated, which supports the concept of scaling. With that, thank you. And if you want to contact us, our email address is here. Otherwise, we will be available at the speaker corner. We also have a Teams channel, which is BlueHat 2019 LIML. So contact us over there. Thank you.